Welcome to the lecture series on policy gradient methods in artificial neural networks. This video covers how to do policy gradients over multiple time steps. So we return to the graph that's often used in TD learning. We start in a state S. From there are different possibilities. Suppose we have taken action A1 according to our policy, then with some probabilistic law we arrive in the next state, S prime. From there, again with our policy, we may arrive in yet another state, and so forth. On the way, we will collect rewards. So on this first transition, we will get the reward at time t. On the second transition, we will get the reward rt plus 1. And the aim is to adjust the parameters of the policy such that this reward now, reward in the next time step, reward in the second time step, reward in the third time step, and so forth. The dots are inside the brackets. This total discounted reward on average is maximized. We want to change our policy such that the return, defined as this expected discounted sum over future rewards, is maximal. To do this calculation, we will use the log likelihood trick, and it's a bit of a lengthy calculation, but it's really worth doing it because it's the basis of so many algorithms. So please be patient and let me walk you through the calculation. So here is this return we want to optimize, and this return is the sum over all these future rewards, and the sum is, I stop here then after 3, but of course it will continue it will contain many more terms. It will continue for a long way. Now, this is an average over all paths starting from my initial state ST. So the idea is, this is my initial state ST. I get the first reward RT here. This is my next state ST plus 1. I take this action. I end up in a state ST plus 2. And I may get reward RT plus 1 on the way. And then we continue and we continue. So this total expected discounted reward from state S at the very top is, of course, the value in the sense as it's used in the Bellman equation, as it's used in TD learning. It's the value at this state ST. Now, since we are going to estimate this online by running through this path from ST, and what I've shown here on the right hand side is just one path, say the path in one of the trials. Since we estimate in the end from these online explorations of the paths, the V that we get from this estimation is a V hat just because it's an estimation. And then very important is the following observation. This estimation will, of course, depend on the way we play. It depends on our policy. So this depends on the policy P. Now, we have seen when we discussed the Bellman equation and the TD methods, that with the Bellman equation, this kind of equation can be formally rewritten in the following form. I can say I sum over all the possible actions that I can take here at the first step, actions at time t, and these actions are taken with a statistical weight that's given by the policy, and the policy depends on parameters. And then I will end up in a next state as prime, but there's some stochasticity, so I have a transition probability with this action that I chose, st to s prime. And then we have the mean reward I get on this one transition, on this first transition. I said the specific reward in one trial is RT, the little r. I use the big R now here for the expected reward for this transition under action A from ST to S prime. And now I'm here in this state, and if the total value in state ST is denoted by this V hat estimate at this location, then there is another V hat estimate at location S prime. And so we can just add this plus gamma V hat estimation at location S prime. And then I can close this bracket. Now, this I highlighted already that this estimate depends on the policy P. And so this estimate here also depends on the policy P. Just keep that in mind. Now what I pulled out here with the Bellman equation is what I call the natural statistical weight of this first transition starting from my state S at time t. Now let's maximize this return, this average return. Let's maximize this value of the state, the estimated value, by changing the parameters. So we now want to change the parameters to optimize this, and let's now do this calculation. So I will change the parameters delta theta, alpha, that's my learning rate. I make gradient ascent. I walk proportional to the gradient with respect to this parameter. V hat estimation P, and in this state ST. Okay, let's do this. So I have alpha times, and then I copy here the different actions, sum over the actions that I can take in time step t, and now I use the log likelihood trick. I have a dependence upon the parameters of this policy, and I take the derivative by copying this policy, p theta at st, and then I add the derivative dd theta logarithm of p at st. So this is just the rewrite of the red terms in the previous line in the form of a derivative of the log policy. And now I can copy the remaining terms. So I will have, well, there's still a statistical weight, so I write it in red. P of ATS to S prime. And then I copy this, R ST to S prime plus gamma V hat of S prime. It's an estimation. And I write the index P. So are we done? No, we are not done. This is not yet the gradient because this term here also depends on the policy. So if we go back to the equation here, we actually, when we take the derivative, we have to use the product rule. There's a dependence here, and then there's a dependence there. We only use the first term so far. Now, let's use the product rule. For derivatives, and this gives that there's another term plus alpha, and in that case I just copy the red terms from the start equation, so it's P theta ATST S prime PAT ST to S prime, and then I take the derivative inside this black brackets over here. The first term is a constant with respect to the parameters. It does not depend on my choice of parameters. It does not depend on the policy. So what we still have is the second term. So gamma, and then this gives the derivative with respect to the parameters V hat estimation S prime, and this depends on the policy. Okay, now this suggests that we now have an iterative procedure. We have to expand this iteratively. I have on the left-hand side the derivative of the value function at location st, and on the right-hand side I have the same term again, but now at location S prime. So this was the detour via the Bellman equation. But the aim is to go back to an online rule. And so now let's work on the online rule. So we have in the first term here, we have the natural statistical weight coming up here and coming up here. So when we play, always from the same starting state, the game several times, then we will choose actions according to that policy, and we will end up in the next states according to this transition probabilities. So this is the things we are going to drop. And the same in the second term, the same statistical weights also turn up. So these are the terms we are going to drop. So we drop the green terms. And then what we have is delta theta equal alpha dd theta logarithm p action given state st. That was this term here. And then we have, when we go online, we no longer have the mean reward for this transition, but we now have the actual reward, the one reward we actually get in this one trial on this transition. So let me write this. This is the reward at time t. Now, this would still be in, what's remaining is this gamma times v hat, but this would still be sort of a batch time model. It's not a real policy gradient if we work with values. So we will replace this by the expression that we had in the first line. And we see that the value starting at state S prime will contain terms RT plus 1, RT plus 2, and so forth. Now this has a gamma in front, so we exactly in our online estimation we get gamma RT plus 1, then we get gamma squared RT plus 2, we get gamma to the power of 3 RT plus 3, and so forth. Are we done? No. This was the first line of this equation. Now let's continue with the second line. The second line, I will write it just below, plus alpha. It's just a copy of this alpha. Then the statistical weights and summations will go away. And then I have a gamma from here. And then we said, well, the term we had estimated at location S prime, taking the derivative of this, actually is iteratively the same formula as the one we just wrote down. So I can just copy now the previous line and say dd theta logarithm of policy. I said I copy, but I need to shift it by one time step. So it's now at plus 1 st plus 1. We need to shift everything by one time step. So I get here RT plus 1 gamma RT plus 2 plus gamma squared RT plus 3, and then we continue. So when we take the gradient of these mean value functions, we get into an iterative loop, and we'll have policies and derivative of policies at location st and action at, plus a term at plus 1, st plus 1, plus you continue iteratively another derivative at plus 2, st plus 2, and so forth. So what we have seen is that the calculation yields several terms of the form of this form here. And what I had written was RT plus RT plus 1 plus RT plus 2. But if you think about this, this is the total return that you get starting in state ST with action AT. So this is the total return in one single episode, in one single trial, starting at state ST with action AT, and you continue to the end. And this was the first term, and I said there are several terms. Then there's the next term. This is then the total return from the next state, and then there will be yet another term, and yet another term, and yet another term. And so this gives rise to a pseudocode for an algorithm that's reinforced. This is the classic policy gradient algorithm for multiple time steps. We have different states, S0, from there we go to S1, S2. We generate an episode where we go through these different states until we are at the end. The end will occur at time S at location ST. We collect the different rewards on the way. And each time we calculate this total return. And let me just write this now as a return. This is what I called on the previous slide, the return from a given state to the end. The end is characterized by this big T. And then we update the parameters with this formula here. And we do this in a loop. So it's not just one term, it's a loop. For each step of the episode, we have one of these terms. To summarize, we start at a state S, which we call ST. Then we play a single trial. We walk through the graph on this trial like this. And what we find is, in order to optimize the return of this state up here, the state S, we have different terms, different log policy terms at AT-ST, AT plus 1, AT plus 2. And each of these terms is multiplied with the returns, where the returns are the total sum of the rewards starting from these different states. So here it's the total return you get starting here, and then you have another return starting here, you have another return starting here, and so forth. And then, of course, everything is discounted, so this gets a gamma squared, and this gets a gamma. So these log policy terms that you see in algorithms are a natural consequence of policy gradient methods over multiple time steps.